Right. Question number 1. This is spring 22. Okay. Right. When a negative charge moves in the direction of electric field. So this is kind of opposite of what we did with the last year's exam, right? Now, because here we have a negative charge, direction of the electric field. So for a negative charge, by itself, if it allow by itself spontaneously, it will move towards the positive direction. So electric field is from the positive to the negative side, right? So let me draw the electric field line like this. Let's say it is to the right. So we have a negative charge, and it is moving in the direction of the electric field. That means it is trying to go this way. So actually, we need to do work to make it go in that direction, right? Because it is like it is trying to go towards the negative side. Electric field is from the positive side to the negative side. So it is repelled because that is negative side. So the negative charge we need to do work. That means its potential energy will increase. Potential energy will increase. So the field does negative work. We will be doing, the external force will be doing positive work. So its potential energy will increase. So this is wrong because it says field does positive work. No, electric field will be doing a negative work, okay, because the external force will be doing the positive work. The field does negative work, that is correct. Field does negative work, that is correct. So either C or D. This is wrong. Zero work is also wrong. So, okay, now we look at these two, C and D. The negative and the potential energy increases. So that is correct. This is wrong. So the answer is C. Number 2. Uniform electric field E of magnitude 200 Newton per Coulomb directed toward the left B to A as shown in the figure. These 2 points are separated by a distance 0.2 meters. What is the change in the electric potential as you move from A to B? So he's asking for delta V. So tell me the equation. Okay. Negative, yeah, I put the negative. The potential difference. So he's asking for the potential change in the potential, mean potential difference, right? Change. So is equal to negative E dot D. If E and D are in the same direction, E dot D will be positive. If E and D are in the opposite direction, E dot D will be negative. In here, E is this direction to the left, and the displacement, because you are going from A to B, so the displacement is opposite. So E dot D will be also is negative. The cosine theta is equal to 180. So that is what makes it negative. So this is negative, and this is another negative in front of it that will make the delta V to be positive. So, and the answer, I mean, how do you get the E dot D? E dot D will be ED cosine theta. Theta is equal to 180. Okay, that's why it becomes -1. And E and D, E is 200 Newton per Coulomb, and D is 0.2. 200 multiplied by 0.2 will be 40, right? Yeah, plus 40. So the answer is number 3. 2-point charges of -2 microcoulomb and +6 microcoulomb are placed along the x-axis as shown in the figure. What is the electric potential at point P? So from this and from these 2 charges will have a potential at the point P. So the total potential will be the potential from both of these charges. So let me call one of them as V1, the other one as V2. And then you need to remember this equation. If you don't remember, well, it is in the formula sheet. The potential due to a point charge is kq over r. So if we have q1 at this point, let me call this as q1 and this one as q2. So I will just substitute the values. Q must be substituted with the sign. K and R are magnitudes, okay? So I can say K, K is a common here. Anyway, let's take the calculator and do this straight away in the calculator, okay? So let us identify what is Q1. This is Q1 and this is Q2 with the sign, okay? They should be with the sign. And R1 will be this guy and R2 will be this guy, same, okay, good. So we can do some simplification if you want because K and R is the same. So I can take it as common factor. So it will be Q1 plus Q2, but this has to be with the sign. So K is equal to 8.99 10 to the power 9 and R is 0.5. Make sure about the SI unit. Here they are all SI unit. Q1 with the sign. That's where, you know, -2 and +6. But don't forget the micro. Okay, so if you do this, you should get the answer. Can you tell me which you want me to do? Oh, you're good. All right. Okay. Anyway, let me also get this. Since I am recording it, maybe it is useful to someone. So I will go there. 8.99 10 to the power 9. Bring it down 0.5. Go up. Multiply. -2 plus 6 will be +4. Okay. So 4 exponent -6. 71920. That means 72 kilovolt, right? Is it there? Is it positive or negative? Positive. We get a positive answer. Okay, next. Question number 4. 2 point charges of 2 microcoulomb and -2 microcoulomb located 1 meter apart. What is the minimum amount of work needed to move the charge apart to double the distance between them? So these two charges Q1 and Q2, initially the R is equal to 1 meter, then we change the distance to 2 meters, double it. So the same two charges Q1, Q2, Q1, Q2. This is initially, this is finally. So the potential energy 1, this is potential energy 2. The work done will be simply change in the potential energy because there is no other energy change. Kinetic energy doesn't change. That's what we are going to hear. So the minimum amount means that we are assuming no other changes except the potential energy change. So the equation for the potential energy is for two charges that you can get from the formula sheet is this R. Q1, Q2, R. Q1 and Q2 must be substituted again in with the sign. Okay, so it will be K Q1, Q2 final potential energy, which we have R2 here, R1. So I will put R1 and R2 here minus K Q1 Q2 divided by R1. Now all you have to do is to take your calculator and substitute. So again, like, you know, this is a common, right, for both. So factoring out will help us greatly in doing the calculation fast. So it will be 1 over R2 minus 1 over R1. Now let me take the calculator and I will just plug in the values into this equation. So work done is K will be 8.99 exponent 9 multiplied by Q1, okay, with the sign. This is very important that not to forget that, okay, -2 plus 2. So it will be, well, you can, let me do the plus, okay, 2 exponent micro, right, and the minus, oops, minus 6 multiply, I better put this in the bracket because I want to bring in the negative sign. So again, 2 exponent minus 6, I will close the bracket. So it is not subtraction, it is multiplication. Okay, multiply, then you start the bracket, parenthesis, and bring this fraction. So 1 divide by R2. R2 is 2. Bring it up. Minus fraction. This is 1 divide by 1. Okay, just 1 anyway. So let me just be complete. Close this. I think I got everything right. The units are good. I converted everything to SI unit. Okay, so press this ST thing to bring it to decimals. 0.01. Yeah, no, it is there. What happened? This is in joule, right? But the answer is in millijoule. So if you multiply by 1000, it will bring it to millijoule. So it will be 17.98 millijoule with the positive sign. So the answer is D. I hope I got it right. Okay. Okay. Question number 5. Each plate of an air-filled 6 microfarad parallel plate capacitor stores 58 microcoulomb of charge. How much energy is stored in the capacitor in joule? So equation, the energy stored, the electrical energy in a capacitor is given by U or E or PE, whatever it is given by, it's in the formula sheet. You start with this half Q delta V. This can also be written as is that right? Yeah. Yeah, so it can also be written as, if you use the definition of capacitance, delta Q over delta V over Q. So this is the capacitance. So in terms of capacitance, if you substitute Q is equal to delta V over C, you will get, can you help me? You have 1 over 2 CV squared. And also another one, if you half again, right? Yeah, that is the half I put here. Let's see. Same thing. Okay. Right. Which one should I use here now? What is given to us? Q. Okay. This is Q, and this is the capacitance. So we should go for this one. Okay. And you know the answer? Tell me. Let's do it quickly just to make sure. Okay. Right. So help me. So okay, let me put this fraction. So Q squared, which is 58 microcoulomb, right? 58 exponential minus, I'm sorry. Okay, I believe I don't need it. I hope so. Okay, but you better, better to put it. But let me check, right? In case. So you already have the answer, so I can check. Okay. But don't take any risk. Okay, now we are not in an exam. So divide by 2 multiply by C. No, Q squared over C. No, there's a 2 here. I bring this 2. Okay, multiply by C is how much? 6. You see, the beauty is, no, it is squared. Okay, 2 multiplied by what is the 6 microfarads? 6 exponent, micro mean -6. Let's see. Yeah. Yeah, I got the same answer, hopefully. A is the answer? Yeah, okay. Yeah, but don't take a chance, okay? Because in an exam, because I knew kind of it is okay, but that's why I did that. It's automatically when you have the exponent, square will be for the whole thing. Okay, luckily. If a question you calculate that has the SI unit of ampere second, you know that, right? Yeah, it is charge. Because the definition of current is what? The ampere. Definition of current is delta Q over delta T. So this is the ampere and this is second. So ampere second will be charge. This is also a very standard question. I repeat every time. So the reason is this, right? Is electric field that is moved. Number 8, internal resistance of an ideal. It's also sometimes repeating statement question, so we don't have to spend too much time on it. So voltmeter should have an infinite resistance and ammeter should have a 0. Okay, so this is out, infinite, and A is the answer. Number 9, for the circuit shown in the figure, the voltmeter reads 8 volt and the ammeter reads 4 milliamperes. What is the resistance of the resistor R? Okay, now this is a meter and this is a meter. This has infinite resistance, right? So that means the current that comes out of this all of the current will go through the ammeter, which is supposed to have 0, it's like a wire, superconducting wire, and there will be no current through the voltmeter because it has infinite resistance, ideal one, and the same current will flow through the resistor. So we have a simple circuit, so we can say E is equal to I. What is the question, by the way? What is the resistance? So E is equal to I R plus R, right? E is given, I is given. No, this is the, E is not given actually. What is given is this V, voltmeter. So this voltage is given, the voltage across the resistor. So this is not going to help us. You will say the voltmeter reading is equal to current multiplied by the resistance. So the current is given and the voltage across the voltmeter is given. It's a very easy question. So R is equal to the voltmeter reading 8 divided by the current through that, which is 4 milliampere. So you have to be sure to put everything in SI unit. That will give the answer what? 2 into the minus 3. A. 10 to the minus 3 when it comes up will be 10 to the plus 3. So kilo ohms. Number 10, an electric heater is operated by applying a potential difference 220 volt to nichrome wire of total resistance 24 ohms. If the heater is operated for 35 minutes, how many kilowatt hour consumed during this time? Right, okay, so the power is equal to, we are given, well, I mean, let me write the whole thing. I mean, this is, you say it is equal to, the first definition is this, right? I delta V. So if I and delta V is given, then, but the thing here is we are given the potential, yes, and is the current given? No, the resistance is given. So using the Ohm's law, this can be translated to I squared. The current is not given. So delta V squared divided by R. So this is the equation we should use for the power. So power is we know delta V squared over R. So delta V is given, R is given, but we need the consumption of the energy. So power multiplied by the time will give you the energy. So let's go to the energy straight away. Right. So substitute now. Let's put the values in 220 squared divided by R is 24. This will be in joule, right? This will be in watt, not kilowatt. So since I want the energy in kilowatt hour, so I can get the price. We need to convert this watt into kilowatt. To do that, I have to multiply by 10 to the minus 3 or divide by 1000. Multiply by the time, 35 minutes. But I want convert that into hours. How do you convert the minutes into hours? Divide by 60. So this will be kilowatt and this will be hour. So we get the energy in the required unit. Right. So we got the energy in the required unit. Then he's asking for, that's it. That's the question. So we have the answer. So let me also do it. Right. I will do this to 20 squared, come down, 24, go up. Now I know it is, so I will do this 1. Okay, first I have to put the multiplication. I'll put 1 exponent minus 3. So multiply by, I will use the fraction again, 35 divide by 60. That's it. Exactly what is there. I will do the same thing. Now here you have to be careful for this 10 to the minus 3. In the calculator, you cannot just get the 10 to the minus 3. So I have to use 1 x minus 3 equal. So the answer is C. Number 11, 18 ohm resistor is connected across a 10 volt battery having an internal resistance of 2 ohms. What is the current drawn from the battery? So we have a battery which is not ideal. It has its own resistor inside the battery. So let me call it small r, and this ideal separate in one ideal cell and the internal resistance. So this is 10 volt and this is 2 ohm, and this is connected to an external load or external resistance, 18 ohms. What is the current? So simple equation again. So we have a simple circuit, one loop. So we can say E is equal to I R plus R. The question is the current. So this is given, this is given, this is given, find this. You don't even have to do the algebra. Yes. Same thing, right? Yeah. Yeah. Let me see what you are telling me. So you are telling delta V is equal to E minus IR. Is that delta V is the open circuit voltage, right? So is it given in the question? No. So, but you know, open circuit voltage will be I multiplied by R. So you are getting the same, right? So that, you know, sometimes it can get confused with the question, because sometimes the question will give you the open circuit voltage without giving the load resistance, and you will take this equation and you will be looking up and down. It didn't give me, how can I find the resistance, right? So that is why you need to know what we mean by the open circuit voltage. Open circuit voltage is the voltage that appears across the outside the circuit, right? So right. So you need to know this. Good you asked me. Okay. So but here that is of no use for us, right? If you just take this equation and you're going to look at it, and where you will be looking in the question, where is the open circuit voltage? It's not given, right? Good. All right. So what is the answer here? Oh, there is some problem here. This is an ampere, this is an ampere, this is milliampere, milliampere, ampere. Okay. I hope I didn't make a mistake in the question. It was, let's say the answer is there. So let me take my calculator. It's there, right? Anyway, just for my satisfaction, I'm going to do it, okay? So E is 10. I will use the solving alpha. Okay, equal, I is the unknown, right? I is the unknown, yeah. So I will put alpha x multiply, then small r is 2 plus big R is 18. Close the bracket. Now I will solve it. That's not the answer. I have to 0.5. Is there? E is the answer, right? 0.5. Okay, good. Right. Question number 12. When unequal resistors are connected in series across an ideal battery, in series, resistors, not capacitors, okay? You have to remember all that. Then you know what is the same when you connect in series? The current is the same, right? Let me go through statement one by one. A, the equivalent, it's about the equivalent resistor circuit is less than that. No, that is wrong, because they are in series, and for resistors it becomes adding the two, right? So that is wrong. B, the same power is, no, that is wrong, because the same current, but the resistors are different. That means the power will be different. I squared R is the power. So this is also wrong. B, C, the potential difference, no, that is for parallel. So this is wrong. D, the equivalent resistance of a circuit is equal to the average of all. No, that is wrong. We know that. The current flowing in, that is correct. Good. Number 13, consider the circuit shown in the figure. Note that two currents are shown. Find the current through the 5 ohm resistor. So this guy, right? So he is asking what is the current through this. Since 2 is labeled here, 1 is labeled here, so best thing is to call it I3, right? Because I1 is taken, label 1 is taken, label 2 is taken. So let me call that current through 5 ohm resistor as I3. Now, you know, two currents are given and there's only 2 loops here. So ideally, I mean, looks like, I mean, we have to use the junction rule. So there are, is this a junction? No, it's just a bend, right? This also. So B is a junction, E is a junction. This is not a junction, this is not a junction. B and E, either you choose B or you choose E, you'll get the same answer. So let me apply the junction rule at B. So I in is equal to I out at junction B. So I stand here, and if you take this segment of the wire, it is no junction there, right? It's the same continuous wire. That means it's the same current in this blue segment. So here it says 4 amperes. That means it will be 4 amperes. This will be I1 coming towards the junction B. And this is I2. So this piece of wire has the same current, and it is I2. So I3 is the one we need to find. Okay. So do we know I3 is coming in or going out? We don't know, right? We don't know. I mean, by looking at, because I1 is coming in, I2 is coming in, it has to be going out. There is no other way, right? So in will be I1 plus I2 is equal to I3. Very simple. So this is plus, because we take the in as positive. This is also plus. So I3, you get the answer 8. Also we get a plus. I'm coming to that. Let me finish this. So you get positive 8, right? That means we know it is out. So that means it is going from, so A is the answer. Now, let me answer what you are saying now. Let's say I didn't think too much, okay? I want to do this question very quickly. So I will say in is, okay, we know 4 plus 4. And I also think I3 is also in. I'm in a hurry. So it is also, I say I3. Then I put it like that. I imagine I3 is also into the, okay. What happened now? When I calculate I3, what do I get? You know what it means? took the wrong direction because for me, I is all magnitude, no sign. Okay, so that's what we are going to assume. I has no sign. Okay, it's just magnitude only. So since I got a -8, that means I did something wrong. What did I do wrong? I chose the wrong direction for I3. I choose the I3 to be into the circuit, but since I got a negative answer, now I know no. So my actual direction is to opposite to the direction I chose. So the current is actually going out. That's how you resolve this problem. Okay. Yeah, because the way we are choosing here, I as magnitude. So I already know I is going in. So therefore, I apply into the junction rule. So this is +4 because it's going in and so on. Okay, so that's how you. So if you get a negative answer while applying the Kirchhoff rules, so what is the conclusion if you get a negative answer? I have chosen the wrong direction, so you flip the direction, that's all. Number 14. Consider the circuit shown in the figure. Note that two currents are shown. Calculate the EMF E1. So he's asking to get this guy, right? So now again, we have two-loop circuit. So two-loop circuit means I can get 3 loops, more than the number of loops we have. Yeah, outer loop. The left loop, the right loop, and the outer loop. So which one should I take to answer this question? Is it about the junction rule? No, you can think. There are two junctions here. The question is about the E, right? Junction rule will only deal with currents. Obviously, it is the loop rule, not junction rule. We have to choose the loop. So out of the loops, we can imagine this loop, let me call it loop number 1. This loop, let me call it loop number 2. And the outer loop, let me call it loop number 3. Which one should I choose? 3. Why do you say that? Because all the numbers are given, there is no unknown. Only unknown is what we need to find. Very good. So you get the answer right. Okay, right. Did you do you did it on your own, right? Okay, very good. So we'll go to, let me delete this so I don't confuse. Right. So we will take the outer loop. So what is loop rule? Some of all the potential changes, you start from A and come back to A. You have to go a cycle, right? So you're going to start from A, here A. So that means you essentially you will be doing this path. So I'll break it down so it's very clear. You'll go to A to B to C to yeah, A, B, C, D, E, F, right? It's D and E and back to okay, F and back to A. So this is a cycle. We are going, say, clockwise. We have chosen to go clockwise. Doesn't matter. You will get exactly the same equation multiplied by -1. Yeah, you know, if you have, for example, if you have 1 plus 2 is equal to 3, if you multiply both sides by -1, -1 minus 2 is equal to -3. Both are correct. So it doesn't matter. So both equations are correct. Okay, so it doesn't matter which direction you choose. But once you have chosen the direction, you have to be careful you don't switch back and forth. You have to remember which direction you are going. That is very important, right? So you can say, okay, now let me just start from A. You go from A to B. Is there any potential change when you go from A to B? Yes, because there is a resistor. So it will be the current is I1, right? In this section, in this segment of the everywhere here, it is the same current and it is going up here. That means here it will be going like this. You are also going from A to B. So it will be I1, I140. They don't have a label for that resist, not 40, 4. Sorry. I1, 4. All right. But here you have to pause, right? Because this is only the magnitude, the sign. If the way you are going is the same as the current direction, it is negative. Okay. Good. So let's forget the physics, okay? We just remember it, okay? If you are going in a direction, the current is also going in the same direction, it's a potential drop, okay? The potential is decreasing because current always flow from higher potential to lower potential. Shall I put the number? Yeah, let's put the number, okay? So because of 4 is the current, resistance is also 4, right? Negative. Next, from B to C, there is nothing. C to, let me call it X, C to X, there is something. It's a potential 20, right? It's 20, right? Yeah, it's 20. And you're going from the positive terminal of the battery to the negative terminal. The potential is decreasing, so negative 20. Then from X to B, we find resistor. Now, let me do something just to make it very clear for people who are looking at the recording, hopefully. In this red segment, it is the same current, right? Because there is no joint branching here. So the current here is I2 in this direction. That means the current will be like this, I2. Okay, now let me go back to the blue color. Right, so this will be I2, you know, the I2 is 4 amperes again. So 4 multiplied by 6. That the resistance is 6. Now, you are going X to D, but the current is flowing D to X in the opposite direction, so positive. Anything here? No. D to E, nothing. E to F, there is this guy now. Current is the same current I1, not I2, right? Current is going this way, and you are also moving in the same direction. So it is 4 multiplied by 4 with a negative sign. And now we come to this last one. This you are moving from F to A, and you are jumping over this cell. It is from the negative of the cell to the positive, so it is positive E1 equal to 0. So you got the equation now. All you have to do now, don't worry about the algebra, let the calculator do the algebra. So you just type this equation into your calculator. So this you can do very quickly because you have your to save time. So 4 into 4 is 16, you can minus, okay, minus 16 and minus 20 and plus 24, right? 6 into 4 is 24 and minus 16 again and plus the x, the unknown, and equal sign. Oops, what did I do? Alpha equal 0 and shift calc, okay, 28. Right. Question number 15.
This is discharging of a capacitor. There is no battery, you don't see any battery. So the capacitor is initially charged. It is charged and the voltage across the capacitor is given 65 volt. And the capacitance of the capacitor is given 24 microfarad. So the initial charge on the capacitor will be Q0 equal to C delta V. C is 24 microfarad and delta V is 65. And if we use your calculator, so that will give me 24 multiplied by 65 to be equal to 1560. Since we put this in microfarad and this is in volt, this will be so many microcoulomb. I didn't bother to change it to Coulomb. I'll tell you why in a minute. So the switch is closed at t equal to 0. So the question is when the charge reduces to 480 microcoulomb, starting with 1560 microcoulomb. So if you go to your formula sheet, you will find the equation for discharging of a capacitor is given by this equation. Q at any time t equal to its initial charge e to the power minus t over the time constant tau. So you should be very careful here. You should not mix up equation. First thing to understand, read the question carefully. You don't see any batteries in this circuit. So there is a charged capacitor and it is being discharged through this resistor by closing this switch at time t equal to 0. So this is the equation you should be using. So now it's a matter of substitution. And the question is to find the time at which the charge becomes 480 microcoulomb. So you substitute 480 microcoulomb. I again did not convert it to coulomb because I'm going to substitute Q0 also in coulomb, microcoulomb. So this is microcoulomb and this is microcoulomb. So it doesn't really matter. If you are going to convert it to coulomb, you're going to divide this, multiply this by 10 to the minus 6. This side also by 10 to the minus 6. So it doesn't really matter. The same factor on both sides of the equation. E to the power minus t. The t is the unknown here. So we need to find at what time t the charge becomes 180 microcoulomb. Divide by the time constant. So for a RC circuit, the time constant is R into C. The value of R is given 1 mega ohm and value of C is also given 24 microfarad. So let me do this calculation separately to find the time constant. R is 1 mega ohm. Mega ohm is 10 to the power plus 6 and C is 24 microfarad. That will be 10 to the power minus 6. Micro is 10 to the minus 6, mega is 10 to the power 6. So it is 2 going to become 1 when you multiply 10 to the power plus 6 with 10 to the power minus 6. 6 minus 6, 0. 10 to the power 0 is 1. So we simply have to multiply them. So it will give you the answer as 24 seconds. Right. So now let me continue with this equation. 418 equals 1560 e to the power minus t divided by 24. 24 is in seconds. So when you solve this equation for the time t using your calculator, use the calculator in the solving mode. So that will make your life easy. You don't have to find the anti-log, inverse log, and so on. You'll get the answer straight from the calculator. So I believe the answer is 28 seconds. Let me check it. My calculator. 480 equals 1560 shift lane minus x for the t down RC is equal to 24 seconds. I will solve this shift calc. Yeah, 28. So time is equal to 28 seconds.
A proton moves along the y-axis. It enters a region in which there is a magnetic field directed at an angle of 30 degrees with the y-axis and lying in the xy plane. Find the initial direction of the magnetic force on the proton. Okay, that's easy. V cross B will be down, and it is a proton, so still down. So the answer is negative z-axis. It's bothering me, that question. Number 17. A charged particle that is moving in the static uniform field may experience a magnetic force, but its direction of motion will not change. Yeah, if we have a particle, charged particle, if it is moving in a static uniform, it will experience a magnetic force. Okay, may. Sometimes it may not. If it moving parallel to the magnetic field or anti-parallel, it will not. So the may is good. The direction of motion will not change. That is wrong. Direction of motion will change. It depends. Okay, may change. B. So this is wrong. May experience magnetic force, which will cause its speed to change. Speed never change. Magnetic force cannot change the speed. It will only change the direction. So he's wrong. Will always experience a magnetic force? No. Sometimes it will not if it is moving parallel or anti-parallel. D. May experience magnetic force, but speed, that is correct. This is wrong. Okay. Question number 18. A path of a charged particle moving with the velocity vector at an angle of 30 degrees to a uniform magnetic field will be helix. Because it is not 0, it is not 90, between, so it's helix. 0 mean what happened? It will be a straight line. Okay, it will continue with the same velocity, whatever velocity. If it is 90, it will be a circle in between. You want to go now, or I can continue? Let's say, okay. A 5-turn circular coil of wire is centered on the origin of its xy plane, and the coil has a radius of 0.225 and carries a there. So find the magnetic direction of the magnetic torque. So we have to find the torque, right? So we go like this. Torque is equal to mu cross B. So vector, right? So mu, the magnitude will be mu B sine theta. Is mu given? No. But we can find the mu. This is NIA. So I can put it like that. NIA B sine theta, because I know mu is that. Okay, so I can get the magnitude first. Let's go to the direction later. So N is 5, I is 1, and A is pi r squared, R is 0.225 squared, and B is 0.4, and theta is what? Theta is the angle between B and mu. So we need to know the direction of the mu now. The current is flowing looking from above counterclockwise, so the mu direction will be along the z-axis, and we already given the angle between B and the z-axis, which is theta. So we take that value, 60. Do you have any issue with the direction of the mu? It's fine. Yeah. You look from above. Z-axis is vertically up, right? So put your eye here. So looking at the coil is a ring, and curl your fingers in the direction of the current, and the thumb, because it's perpendicular to the plane, right? Either positive Z or negative Z. So it is counterclockwise, so it will be positive Z. So now we know mu direction, and B is making an angle of theta with the mu direction, and that theta is given to us 60, so that's what it is. So let me quickly calculate it. Mm, 5 multiplied by pi. Oh, what did I do here? Okay, 5 multiplied by pi multiplied by 0.225 squared multiplied by 0.4 multiplied by sine 60, close the bracket, 0.275. So you got that. Only B and C has 0.275. So we can eliminate all the other answers. Direction, right. Mu cross B. Mu cross B. B and mu are in the plane ZX. Because B is making it, we say in the question, magnetic field B is in the plane, where does it say? XZ plane. But B, where is it B? A point for that directed angle to the from the positive Z direction and a component only in the XZ plane. So it is in the XZ plane. There's no component in other XY direction. That means the mu B plane is perpendicular to Y, right? So it must be the direction of mu B, mu cross B, either positive Y or negative Y. Right hand rule, put your finger in the mu direction. So you curl it is towards B, so it is toward the positive Y, right? Positive Y. Is that okay? So we put our hands in the mu, the first vector, mu, and make sure you are curling it is in the ZX plane. Your curling must be done in the ZX plane, so you can curl it towards the B through the small angle, and your thumb is pointing to the Y direction. Positive. It depends on what you mean by, shall I use this board? Oh, you show me. Okay. I am the Y. Okay. X is to Y. X is towards me. You want to X is towards me? Yeah, towards me, and look at the thumb. Yeah. Positive Y. Okay. Okay, good. Right. So that make B out, and C is the only correct one. Number 20. A current in a long straight wire, that you know this answer, right? Let's see. Number 21, because this is either you know it or you don't know it. Okay, so this number 21. A negatively charged particle is moving to the right, directly above a wire, having a current flowing to the right, as shown in the figure. In which direction is the magnetic force exerted on the particle? Right. Can you do it? Okay. Right. Why? Yeah, a charge, right? A charge is the question is what? The magnetic force on this charge. What is the theory? If you have a charged particle moving in a magnetic field, it will may experience a magnetic force. Okay, this is the theory. So you have a charged particle. Is there a magnetic field? How? Where is the magnetic? So the function of the current is to provide the magnetic field. So it's like a magnet, right? So this magnet, so-called magnet, the wire carrying a current, it's like a magnet. It's going to give an external magnetic field on this charged particle. So what is the direction of that magnetic field? Yeah, so we are combining two concepts, right? So you put your thumb in the direction of the current, and it will be circles around this wire. So at this point where the charge is, so let me call it point P, What is the direction of the magnetic field that is coming from the wire? Out of the, very good, you. So why did you say you don't know? Come on. Shouldn't, I mean, most of the people are overconfident and that is good, I like it, when you are humble, then you will learn, when you arrogant, you think I know everything, you're not going to learn. So, right, very good. So it is out of the plane. You know how to do that? Like this. Now forget about this wire. We don't need it anymore. So now we have reduced the problem of a charge moving in a magnetic field. The direction of the magnetic field is out of the board. The velocity of the charge is to the right. And I want to get the magnetic force. Magnetic force is Q V cross B. So it will be the direction of V cross B multiplied by the charge. If the charge is positive, it will be the same. If the charge is negative, it will flip the direction. So what is the direction of V cross B? V cross B. Down. Is a negatively charged, so it is up. All right. So C is the right. Okay. Number 22. This is a standard answer, right? Opposite to the number 23. Okay. All right. Explain to me. Start from the beginning. How do this has no battery, right? The coil has no battery. But when you move the magnet towards the coil, it will induce a current. Now, Lenz's law says the current will be induced in such a way to oppose the change. Very good. What kind of change is happening? When the magnet is here, there will be certain magnetic field into the coil. When you move it towards it, there will be a change in the magnetic field. So this is south pole mean the direction of the magnetic field through the coil will be to the left, right? The magnetic field that is from the magnet, the external magnetic field. It will be to the left. And as you bring it closer, it will become stronger. So this magnetic field will increase in magnitude to the left as you bring it closer. I don't like it. I mean, I am the coil now. I am the coil. I say, no, don't change. What will I do? I will create my own magnetic field to cancel this change. How can I do that? I should, let me take red now. This direction and it is increasing. To the left and it is increasing. How can I stop? Yeah, I will make an induced field in the opposite direction. So I will use red for my induced field. So induced field must be to the right. Okay, that's the first step. Now, what kind of current I should send so the induced field direction is to the right? Yeah, looking from the left, okay, in the same direction as the magnet, it should be flowing clockwise. The current must be flowing clockwise, looking from the left, okay, left. So from, no, I can be if I here it's also my perspective. So don't say my perspective, look from the magnet's perspective, okay, right? Looking from the left side of this. So let me draw it. The current must be like this, right? So this is the best way. Got it? So through the resistor, it should be to the left. The current must be flowing to the left through the resistor. Which is the answer? Right to left. Number 24. A generator connected to a wheel, the wheel or hub of a bicycle can be used to power lights or small electronic devices. If the generator's magnetic field has a magnitude this, with n is equal to this, loop area this, find the maximum EMF. Right now you need to remember what is this? You are talking AC generator. Go to the formula sheet and you will see an equation for the induced EMF from generator, and be a omega sine theta. The theta can be also written as omega t. So it's a function of the time, right? Theta or omega t. Depending on what we have been given, we can. But here the question is the maximum. Maximum is only this part. So it's simply the maximum voltage is N B A omega. Substitute and find the answer. Can you do it for me quickly? 100. B is 0.8. Make sure everything is SI unit. A is 4.8, 10 to the minus 3, and omega is 20. What do you get? Okay, C again. Okay. Number 25. A current decreasing at a rate of 9.6 ampere per second is flowing through a solenoid having no appreciable resistance. The self-induced EMF in the solenoid is found to be 8.4 volt. What is the self-inductance of the solenoid? So the equation is this. We define the inductance by this equation. Right? This is given 9.6, the whole thing, okay, together. This is the question, and this is given. Okay, so it's a magnitude only, so we don't worry about the negative sign. Sometimes the question can be to get the direction of the, I mean, suppose the question is to find the current, I can ask which direction also. Yeah. Yeah. Decreasing. Anyway, I mean, the question is to find the L, right? L is a magnitude. You don't have to worry too much about the sign here. So the magnitude, L is a magnitude simply. So it will be magnitude E divided by magnitude. Okay. But actually, I mean, there are some exams where you are asked to find the direction also. How do you get the direction? Say this is the coil. It's again the like, it will oppose the change, right? Suppose the current is flowing to the right and it is increasing. It's a bit more than that. The induced EMF will be, it should, suppose it is increasing, the current is going to the right and it is increasing. The induced EMF from this coil should be to the left. Okay. So from that way, so induced EMF to the left means the current from the induced current. Yeah, if you ask, not induced current, if you ask what kind of induced, yeah, that's how you should say. Okay, the induced EMF will be to the left. If it's going to the right and it is decreasing, it's supportive. Very good. Okay, so you get the idea. Check if you have in a past exam any question where you asked to find the direction of the. I can't remember. Okay, so check. Yeah. Sure. 45, of course, you can always write an email, okay, and make an appointment with me. Don't worry, okay, I'll be more than happy to help you. Okay. Number 26, a 45 millihenry ideal inductor. You want me to stop now? No, okay. A millihenry ideal inductor is connected in series with a 60 ohm resistor through an ideal 15 volt DC power and an open switch. The switch is closed at, okay, now what is this? It's a RL circuit. RL circuit, also like the RC circuit, has time constant and equations for the current through the circuit. And again, you go to the formula sheet, and this is also, again, there is whether it is closing or opening, whether it is what do you call it, while it is charging or discharging, and the inductor is connected in series with the, here it is not really about charging. The switch is closed at time t equal to 0. What is the current 7 milliseconds later? So what is the equation for this? This is the current as a function of time. So I is equal to I0. What happens to the current in the case of LR circuit? The current will increase like the charge is increasing across the RC circuit, across the capacitor. The current will also increase. That means this 1 minus the tau, because of LRL circuit, it is not RC, the tau, the time constant will be L over R. Once you know these two equations, then you can just do the question. Let's substitute. Is asking for the I, this is the unknown, giving the time, not the time constant, time. Okay, so given the time, this is the time constant, find the current at that particular time. So this is a direct substitution, not solving equation. I0. I0 is the current that eventually it will come to, which will be simply equal to the E over R. At the end, the I maximum, okay, I maximum, it will be E over R, because the inductor become like a superconductor, no resistance at all. So the only resistance is the resistance of the resistor. So eventually the current will be like this, which is we know. T is given, we will substitute later, divide by tau. Tau is also given, L and R are given. Let's substitute now. Take the calculator. Do the fraction. E is 15 over 60 SI unit, okay, multiply 1 minus shift ln fraction again, negative sign, t is 7 millisecond, right? So since we're going to put everything SI unit, so we will spare the trouble. Let me look at the L and R. Let's just to put everything SI unit so you don't get into any trouble. So time is in milliseconds, so I need to convert to second. Divide by L over R. Let me start a bracket now. And then fraction again to put the L over R. I don't like it, it becomes. So let me use the division sign. So L is what? 45 millihenry. So I will make it into Henry. Milli mean and the minus 3. I use this symbol division. Okay. R is how much? 60 ohms. I close the bracket. These brackets are important. Okay. Probably not. Okay. No problem. That's it. I will calculate that. 0.249 amperes. That means 250 milliamperes. I didn't make any mistake in this one. Okay, number 27. A 30-volt battery is connected in series with a resistor and an inductor with R is equal to 3 ohm and L is equal to 44 Henry respectively. Find the energy. This is just the equation. You just have to know that energy, potential energy or whatever that coming from the magnetic field is equal to half Li square. Substitute half. The resistance is energy stored in the inductor, right? The resistance doesn't matter. It's just there, just to confuse us. Is Henry. Henry is the SI unit. I is I is not given. How do I get the I? I will be there at the end, right? So I will be simply this divided by this. Can you get the answer? 10 square is 100. 2 multiplied by 100 is 200. Okay. Okay, what is the RMS current is equal to the direct current, that is the equal amount of energy in a resistor at the same rate as in, that is how you get the RMS value. 29, in a capacitor in an AC circuit, the voltage lags. No, yeah, lags. Capacitor lags by 90 degrees. Yeah, current. Yeah, you always look at with respect to the current. Okay, what happens to the voltage with respect to the current? Not what is the current doing with respect to the voltage, but what is the voltage is doing with respect to the current. That's voltage lags the current. So suppose I can confuse you by putting the current leads the voltage by 90 degrees. That's also the same thing, right? Okay, so number 30. The current in an inductor connected to an AC voltage source lags voltage. Why? Yeah. The lag is caused by what? Now we are talking about inductor, the back EMF of the inductor. The coil is there. 31. In a purely inductive AC circuit, as shown in the figure, the delta V max is 130 volt. The maximum current is 6 ampere at 70 hertz. Calculate the inductance of the inductor. Right. You know that the reactance of an inductor is given by this. That's in the formula sheet. So why do I go to the reactance? Because I want to apply the Ohm's law. For Ohm's law, resistance is replaced by reactance for inductor and capacitor. What is Ohm's law? Delta V is equal to current multiplied by the, not R. R is for resistor. That's why I am writing that. Okay. Ohm's law is delta V is equal to I into impedance, if in general. So the impedance now is only the reactance. The circuit has no resistance, no capacitance. So only the reactance of the inductor. So is this okay? So what is given are maximum values, right? So delta V maximum is equal to I maximum. This is given. This is given. And the question is to find, not reactance, the question is find the L. But now you know that in the XL there is L. So let me write. The only unknown in this equation is L. So let's do it, yeah? Okay, let's do it. F is given, right? We need F. F is given, 70 hertz. So let me take my calculator. Delta V max, 130. Alpha equals I max, 6. Multiply by, let me put the bracket just to make sure that we don't, we get the equations correct. Shift by multiply by F is 70. Multiply by L. L is the X, right? The unknown. Close the bracket. That's it. Shift, calc. Yeah. So millihenry, right? So its Henry is 0.049. That is 49 millihenry. Number 32. Yeah. So here, if you read the question, it looks like again Ohm's law, right? What is Ohm's law? Z. Let me put it in general. Z is the impedance. Impedance is everything, okay? Resistance, reactance, everything. And the impedance is given by, in general, for a RLC circuit, right? Now here, do we have capacitance? No. So this is 0. can cancel or 0, whatever you want to call it. So that means delta V equal to I what do we have? Our RMS values. Both has to be RMS. This is given, frequency is given. Ah, RMS value of the current is given, I is given, R is not given, XL. Is the inductance given? No. No, XL is given. Reactive inductance is given, but inductance is not given, right? The question is to find the current. Resistance is given here. The question is to find the resistance. Okay, but XL is not given. But can you find the XL? How? Can I write this equation for this? Delta V L is equal to I multiplied by XL. See, this voltage across the LMS, voltage across the inductance is given to us 50. That is this voltage. And the current is also given to us 0.6. That means I can find XL. XL is equal to 50 divided by IL. Are you following me? Did you get that point? So we just go to this because I don't have XL, but I know the potential difference across this and I know the current through that. So just like, imagine this resistance, what will you say? You will say delta V is equal to I multiplied by the resistance. So here I can say delta V across the inductor is equal to current through that multiplied by the reactance, not the resistance, not a resistance. So how much you get for XL? 83. You got this correct? Okay. 83 ohms. Now I can substitute it here. And the only unknown is R. Can you do it? Okay, let me do it too. Delta V, this 30, right? Not 50. 30. Let me clear everything. 30 equals IRMS is 0.6, right? Yeah, 0.6, 0.6 multiplied by, oops, what did I do? It's an equation, 60 alpha equals, alpha equals, IRMS is 0.6 multiplied by, start the bracket, square root Not 60. 130, right? Yeah, I'm sorry. 130. Thank you. 130 alpha equals IRM is 0.6 multiplied by, start the bracket, square root of R squared. That is a question, right? So I'll call it X squared plus XL is 83, right? That's what you said. Okay. Close the bracket. Oops. You don't need the bracket, but anyway, just let me just check my equation. 130 equals shift calc 200. An inductor and a resistor are connected in series. When connected to a 60 hertz 90 volt source, the RMS voltage drop because the resistor is found to be 50 volt with the resistor. Okay. And the RMS current through the circuit is 400 milliamperes. Find the power delivered to the circuit. Okay. Now the power delivered is only, power will be spent only through the resistor, and the power is given as the current is given to us, right? So current squared multiplied by the R resistance. Is the resistance given to us? No. So I RMS V RMS across the resistor. These are given, right? IRMS and VRMS. VRMS given? Yeah, 50. IRMS 400. So it will be 400 milliampere. So it will become 0.4 multiplied by 50. Of course, we have extra data. This. No, that is this. And this is that. They are the same, but we don't have the R. So we have to go for this equation. There's no square there. IRMS multiplied by VRMS, which is 20. What is the impedance of a series R? Because this is, in a resonance. So when there is resonance, this is 0. That will make the impedance to be just R. Question number 35. Transformer question. So you just remember the equation for the transformer as V1 divided by N1 is equal to, am I correct? This is the equation, right? It's a ratio equal. It doesn't matter whether you put up and down, you have to consistent, okay? So delta, what is the R across the secondary? So delta V2 will be N2 over N1 into delta V1. So that will be 450 divided by 225 multiplied by 100. What do you get? 140? 41. Okay, we finished it.